All right, last time we started section 5.1, we had taken a look at addition of integers, and we kind of also looked a little bit at absolute values, talked about that some, and some additional properties that we didn't have before. So we had left off on these properties. That's where we ended, right? And now we're going to start integer subtraction. All right, so integer subtraction is defined pretty much like whole number subtraction was. A minus b is the unique integer as opposed to whole number n, such that a is equal to b plus n. And we can talk about taking, for instance, 5 minus 7, right? We can subtract 5 minus 7, and this will equal some number n, as long as if I were to take 5, it would equal to 7 plus that n. That's what it's saying, right? And what would that n be? Negative 2. Yeah, negative 2. And we did have an additional condition when we did whole numbers that we don't have anymore. The condition was that the value that we were subtracting the front of, the a, was bigger than b. And we had that condition because we needed numbers to stay positive, right? This example shows you an example of one that doesn't actually end up being a positive number when we're done subtracting, and that's okay now because we're now working with integers, which is including the negative numbers. All right, so there are some models for integer subtraction that are going to feel very much like the models for integer addition. They all have the same names and everything. Oh, sorry, one more fact before we get there. Theorem 5.4, my bad. Subtraction is the same as adding a negative. I don't know if you've had the experience like I did, but I actually had, I think it was a 7th grade teacher who flat out told us the entire year there is no such thing as subtraction. She stuck by that. There's no such thing as subtraction. It's always adding the negative, adding the opposite, which is fine. But she was talking about this particular property, right, is that it's adding a negative. So we're going to take a look at integer subtraction with the idea of how you think about subtraction, which most of you, if I said, what is subtraction, you would say what? Takeaway. That's how we usually think about it. So we're going to think about these models in a very much of a takeaway kind of perspective, okay? So just like we did before when we had the chip model, we have, I'm going to have to get my chips going again, we have black chips as positives, and we have red chips as negatives. And again, you can use other colors. It's just that if you do, please make sure you tell me what represents what so that I'm not guessing. So these are my positive chips, and these are my negative chips. So when I'm looking at doing an integer subtraction model with the chip model, it starts by telling me here that I have 5 positive chips. So that would mean I have 5 black chips. And this symbol, whoops, right here, you guys just told me at least one way to think about it is that it's takeaway, right? It's takeaway, it's removing. And we are going to continue with that idea. So we're going to take away, but we're supposed to take away what? 3 negative chips. Does anybody see a problem with that? What's the problem? What's in my circle?
5 positives.
5 positive chips. So what's the problem?
There's no negatives.
There's no negatives to take away. Y'all see that? That's a problem. If I'm supposed to be it's like if I have, in my office when we bring my kids at the end of the day and they really, really, really want grapes and all I have in the refrigerator are apples. What am I supposed to do about that? Well, in that scenario, I tell them tough luck. But here, I need to take away something, right? I've got to remove something that's not actually there. So how am I going to do that? Well, we're actually going to do that by putting in 0 pairs. When we did addition, we were removing 0 pairs. Do you remember that? If we saw a red and a black in there, I could remove them both. Well, it will actually be an equal quantity if I did this. Add a black and a red chip, that's a 0 pair. I didn't change the value. And now I have a negative chip in my circle, right? But how many negative chips am I supposed to have? 3. So I need to do it again. And one more time. So I'm adding 3 0 pairs in because I need 3 negatives to be able to take 3 negatives away. So now I can remove my 3 negatives And what will I be left with? I will be left with 8 positives. And my answer is then 8. And this is a concrete model that shows why subtracting a negative gives you a positive. Right? Subtracting a negative gives me a positive. The charged field model works very similarly. As you remember, charged fields mean that I add pluses and minuses into my circle. So again, I need 5 positives because I start out with the number 5. And then this is again remove or take away. I'm going to write remove now. Remove 3 negatives, but there aren't any negatives. So what would I have to do to get negatives? I have to put in positive and negative pairs, right? It didn't change the value. The circle's value is still 5, all right? But once I remove those 0 pairs, or not the 0 pairs, but the negatives, the 3 negatives, I will change the value of what's in my circle. How much is now in my circle? 8 positives. All right, number line model. So what are we going to do about the fact that I've got 2 negatives? When I talked about negatives before, we talked about turning around and going the other direction, correct? Turn around and go back the way you came from. Agreed? So how does it look for this? Well, I need my negatives to represent one of 2 things. You can do it one of 2 ways. So one way you could talk about it is that a negative makes you turn around. So I'm turning around, what? How many times? Nope. Let me do it. Let me stand up for you. Okay, 5 tells me I'm going to move 5, right? So starting over here with Aspen, I've got 1, 2, 3, 4, 5. I'm going to run out of desks up here, but you can imagine. The first negative tells me to turn around. What does the second negative 2 tell me to do? Turn around again, and then do what? Move 3 more, okay? So that's one way to do it. Another way to do it, again, I'm going to end over here at Jordan, is that when I get to Jordan going this direction, is that the first negative can tell me to turn around, which is fine, and the second negative can tell me to walk backwards. So you can go backwards 3. But now you're going in the other direction because you've turned around. So I don't care which of those perspectives you want to use, but you can see that kids who are standing up on, like this line on the front of the, I wouldn't give kids those choices, by the way. Just pick which one you like and go with it. Okay, but I'm letting you know that there are 2 different perspectives of how you can think about that. So I think your book uses the first one as turn around, and then the second one is go backwards. But if you want to use go around, turn around twice, I'm okay with that. Turn around means to go in the opposite direction, and you do it twice. So on a number line, like in terms of drawing it, it doesn't really draw very well. And that's sort of unfortunate, but it's just reality. So on my number line, I start at 0, and I go 1, 2, 3, 4, 5. And then if I turn around twice, I still end up going 3 more in the positive direction, and there's really not a good way to draw that. Sorry, I'm going 3. I ended 8. Okay, so I lose a lot, really, in the drawing of what I've done physically. That happens sometimes. The pattern model. Okay, so the pattern model, again, when we did patterns before, the idea is to start with something that I know how to subtract, that is whole numbers. So something like, let's say we'll start with 5 minus 2. Okay, you can subtract 5 minus 2, those are both whole numbers, and I end up with 3. I can subtract 5 minus 1, those are whole numbers, and I end up with 2. And I can subtract 5 minus 0, whole numbers that end up with 5. I don't know why that says 2. That should say 4. Goodness gracious. Let me fix it. Thanks. All right. So with the pattern model, the idea is to recognize that as I go down, that was really not good. As I go down this column, the numbers are increasing. So again, and as I go on this column, the numbers are decreasing. So it's 2, 1, 0, and the next number would be -1. So, whoops, that's what I meant to do. So if I continue my pattern, 5, minus -1. The pattern on the right is to go up to 6. 5 minus -2, pattern on the right goes up to 7. 5 minus -3, pattern on the right goes up to 8. And then, of course, the answer is 8 because I got to my 5 minus -3. All right. Not exactly sure why your book places the next topic in this section, but that's okay. We can do it here just fine. This is order of operations. This is not the only order of operations description out there, but it's the one that's probably been around the longest. It's the one that your book uses, so it's the one I'm going to show you and remind you of. Many of you might have remembered acronyms to remember PEMDAS. What's the one you remember?
Please excuse my dear Aunt Sally.
That's the one that I remember too. Please excuse my dear Aunt Sally. Has anyone heard anyone different than that? No? Every now and then I have someone who has. There is a slight problem with the way that this is presented. The problem is that it looks very much like the addition has to happen before subtraction and multiplication has to happen before division. Do you see that? I mean, if I go left to right, that's what it looks like. The problem is that that's just simply not true. So let me identify the letters for you, and then I'll describe what I mean. So what is P for? Parentheses. What about the E? Exponents. M and D are for what? Multiplication and division. And the reality is that there is no order between those two. You can divide before you multiply. You can multiply before you divide. The values will be the same, but you have to move from left to right. So if the division occurs moving from left to right first, you do it first. It doesn't matter that the letters are not quite in that right order. In a very real sense, it almost should look like this. But even that starts to feel like there's still some sort of an order there, and there really shouldn't be. Yes, multiplication and division happen before addition and subtraction, but not necessarily before each other. And then the last one, of course, A and S is addition and subtraction, same thing. It's left to right, not addition and then subtraction. So I have an example of one. It doesn't have any parentheses or exponents in it. But the point that I want to show you with this one is about the ordering that I'm talking about. So on this one, I have 5 minus 2 plus 6 divided by 2 times 4. So which operation am I actually going to do first in this particular problem? Division. Yep. Multiplication and division have to happen before addition and subtraction, and the division occurs first when I read from left to right. So this is my first thing to do. Everything else is going to be rewritten until I do it. So what is 6 divided by 2? 3. So then this is plus 3, and then I have times 4. What would the next thing I need to do be? Multiplication, right. So I'm going to multiply the 3 times 4. So what is 3 times 4? 12. What is the next thing that I would do in this order? It's actually subtraction. 5 minus 2 is 3. And then finally 3 plus 12 is 15. There's some questions in your homework or group work, I can't remember which one, maybe both, that ask you to say what the last step is. What's my final step of all the process? So if we were doing that on this problem, your last step would be 3 plus 12, right? That's what you would write down as my final step, okay? So it asks the question sort of a little bit differently. It doesn't just say solve it. It actually wants you to specifically tell it the last step in your processing. Any questions on that? All right.